5, 4, engine ignition, 2, 1, 0. Relay and liftoff. As the countdown to Mars continues, the perseverance of humanity launching the next generation of robotic explorers to the Red Planet.
On July 30th, 2020, a United Launch Alliance Atlas V rocket lifted off from Cape Canaveral, Florida, carrying the next generation of Mars exploration vehicles, the Perseverance Rover and the Ingenuity helicopter. And today, on February 18th, 2021, if all goes to plan, the two vehicles will land safely on the Martian surface after their long 7-month journey to the Red Planet. Only 40% of missions sent to Mars have been successful, and Perseverance will have to endure a vicious and complicated landing sequence as its creators wait, powerless to intervene, waiting for news of its success back in Pasadena. The Perseverance rover is the largest and heaviest rover JPL has ever sent to Mars, heavier than the Curiosity rover by 100 kilograms, and with that extra weight comes a whole host of new gadgets. This isn't some slightly upgraded version of the Curiosity rover. Perseverance is benefiting from almost 10 years of advancement of technology. It's packed with fascinating and novel technologies that will form a stepping stone in humankind's eventual first steps on the surface of the Red Planet. This is the insane engineering of the Perseverance rover. Perseverance, hopefully, is now safely on the ground, where it will live a long, illustrious life on the Red Planet. We have learned some things from the Curiosity rover that will hopefully help Perseverance avoid the struggles its predecessor is experiencing. We have made an entire video on the struggles of the Curiosity rover wheels and how they've been gradually falling apart on the harsh Martian surface. In the end, the engineers of JPL did not opt for shape memory alloy wheels like the ones we discussed in that video, but simply increased the diameter of the wheels, decreased their width, and increased their thickness, while incorporating sturdier curved threads that will better resist crack growth than Curiosity's sharp cornered threads. They have also foregone the rectangular cutouts which imprinted Morse code, spelling out the rover's origins in the rusty dirt of its new home. There is a whole host of new software upgrades too, like the algorithm that determines when to open the parachute. In the last mission, the parachute simply deployed when the target speed of 1,450 kilometers per hour was reached, after most of the hypersonic re-entry speed of 21,450 kilometers per hour had been bled off. For Perseverance, JPL wanted to increase the accuracy of their landing. So this time around, the chute will open when it is approaching the optimal trajectory for the landing site. It will also be scanning the surface of the landing site and correlating those images to its pre-existing map to allow the sky crane to choose the best landing site with minimal obstacles. Perseverance's ground navigation systems have also been significantly upgraded, with its optical sensors feeding data to a machine learning vision algorithm, allowing Perseverance to find its own path through the rough terrain of Mars, where Curiosity had to constantly stop and start with help from its earthbound controllers. Perseverance is benefiting massively from the past decade of improvements in autonomous flight and driving developed by the drone and automotive industries. This will mean Perseverance will be able to cover much more ground during its life, here in Jezero Crater, a massive crater that was once home to a lake the same size as Lake Tahoe. You can see the remnants of this ancient river bed and delta spilling into what may have once been a habitable body of water. It is here that Perseverance will scour for signs of life. Before we get into all the gadgets it will use to do this, let's look at how Perseverance will power them. The Perseverance rover features the same radioisotope thermoelectric generator as the Curiosity rover. RTGs work by converting the heat from the natural decay of radioisotopes into electricity. It uses a simple principle called the Seebeck effect to generate electricity. The Seebeck effect essentially allows us to generate an electric current through a heat differential, as charge carriers, both electrons and electron holes, will move from hot to cold. So, if we have two semiconductors, one with charge carriers in the form of electrons and one with charge carriers in the form of holes, a potential difference between the two semiconductors will form when a heat gradient is applied. This potential difference causes a current to flow in the external circuit. These two semiconductors need to be both thermally insulating to ensure the heat gradient is maximized, but also electrically conductive to maximize the current. These two material properties are typically linked. Copper is both a great electric and heat conductor, while iron is a poor electric and heat conductor. Having a single material that is a great electric conductor and a poor heat conductor is extremely rare. For this reason, two unique materials are used for the P and N-type semiconductors: lead telluride for the N-type and an alloy commonly called tags for the P-type, which is formed from tellurinium, silver, germanium, and antimony. Now, we just need a consistent heat source. Thankfully, radioactive substances generate heat as they decay. The Perseverance rover uses 4.8 kilograms of plutonium dioxide as its heat source. This radioactive material primarily produces alpha waves, which is essential as this form of radiation is most efficiently converted to heat in a compact space. While plutonium-238 also releases minimal beta and gamma radiation, decreasing the weight of shielding needed to protect the electronics on board from these more powerful kinds of ionizing radiation, an essential characteristic for a lightweight spacecraft. The plutonium-238 is also formable into a ceramic-like material that will break into large chunks, rather than being vaporized and spread in the wind during a launch failure, where it could be inhaled or introduced into the food chain. The electricity this unit can provide will gradually degrade from its maximum of 110 watts at launch as its plutonium heart naturally decays, losing half of its energy every 87.9 years, which is much longer than the 138-day half-life of the early polonium-210 RTG prototypes. Another advantage of plutonium-238 for this application. This will power all of the instruments on board, like the MOXIE, which is one of the new devices I am most excited about aboard Perseverance. MOXIE is a new oxygen generation device that will test a vital technology for any future human mission to Mars. You may wonder, like I did, how is this different from the oxygen generation present in the International Space Station? There is obviously a limited supply of oxygen there. Why do we need to test this new technology on Mars, when we obviously have a tried and tested method of creating oxygen already, surely? The International Space Station does not really recycle oxygen. Oxygen is created on the International Space Station through electrolysis of water. This produces hydrogen and oxygen. The hydrogen is then reacted with carbon dioxide to form water and methane. The methane is then simply exhausted into space while the water is fed back into the system. The International Space Station requires regular resupply of water, as we are losing 2 hydrogen atoms for every oxygen molecule we create. This is not a closed-loop system, and water is a pretty heavy material to be shipping to Mars. The Perseverance rover will test a new method of oxygen creation using this device, which will use solid oxide electrolysis to instead break the plentiful carbon dioxide in the Martian atmosphere into oxygen and carbon monoxide. Its operation is fairly simple. Air will be taken in through a dust filter by a specialized pump designed to be as light and compact as possible, called a scroll pump. Scroll pumps are pretty cool. They consist of 2 spiral scrolls, one stationary and one rotating. Air is taken in at the inlet here, and as the secondary scroll rotates, it traps and squeezes air against the primary stationary scroll. This continues to happen as the volume between the 2 scrolls decreases down the spiral, causing an increase in pressure. In this case, it causes the variable pressure Martian air, which is typically about 100 times lower than Earth's atmosphere, and compresses it to match Earth's sea level pressure. These kinds of pumps are lightweight, energy efficient, and reliable, making them the perfect air pump for the Perseverance rover. The pump feeds the carbon dioxide-rich air through a cell stack. Each stack consists of a catalytic cathode, a solid electrolyte, and an anode. As air passes over the cathode, which operates at 800 degrees Celsius, the carbon dioxide is split into carbon monoxide and oxygen ions, according to this reaction. The oxygen ion passes through the solid electrolyte to the anode, where it is oxidized, combining with a second oxygen atom to form gaseous O2, which is then passed out of the anode cavity and tested for purity. MOXIE can produce 20 grams of oxygen an hour. However, the unit will not run continuously, as it draws too much electricity, which will be needed for another operation. In total, the MOXIE system needs 168 watts, which is actually more than the 110 watts the RTG can provide at any one moment. So, this operation will need to be supplemented by 2 lithium-ion batteries that are included on board to make up for the low-power RTG, allowing it to store excess power during downtime. This device is exciting because it is a clear statement of intent. Oxygen is going to be a vital resource for any future mission. And this is actually a scaled-down prototype of the full-size version NASA eventually wants to send to Mars, along with an empty rocket. The full-scale version will produce about 2 kilograms per hour, which will gradually be stored inside the awaiting rocket over the course of a year and a half, providing life-sustaining air for any future human missions and the oxidizer needed for the ride home. The next device, which is also depending on a future Mars mission to complete its purpose, is the core sampling drill. The Curiosity rover sampling system drilled and scooped soil into this instrument, the SAM, standing for the Sample Analysis at Mars. The SAM is located here on the rover. It contained multiple tools that would be commonplace in many Earth-bound labs: a mass spectrometer, a gas chromatograph, and a tunable laser spectrometer, each looking for different signs of life on Mars. Perseverance has replaced the space this unit took up with a totally new system, the Sample Caching System. The robotic arm of the rover features a coring drill, which will cut out cylindrical core samples from the Martian surface. Once collected, the robot head mates with the drill bit carousel, where it transfers the bit and the sample tube into a rotating carousel that takes it to the belly of the rover, where another robotic arm resides. Here, a number of operations takes place. First, the arm pulls the sample tube out of the drill bit and takes multiple images of it, before and after calculating the volume of the sample. Then, it stores it in one of the 42 slots under the belly of the rover, where they will remain until the rover deposits them in these sample tubes at a designated caching spot on the surface of Mars. This is where things get really interesting. There are plans to send another rover, designed by the ESA, to Mars in 2026. This rover will deliver the samples back to its NASA-designed lander, which will load them into a Mars Ascent vehicle, blasting the samples into orbit where an ESA Earth return vehicle will be waiting for it. We are attempting to bring soil back from Mars with robots. If that isn't insane engineering, I don't know what is, and we have barely scratched the surface of what this rover is capable of. There is a whole host of new sensors on board that do not require Perseverance to collect soil, each using different forms of electromagnetic radiation to investigate the ground below them. The Sherlock instrument on the robotic head will look for signs of biosignatures using Raman and luminescence spectroscopy, which both detect molecules based on how they interact with UV light. It will sit about 5 centimeters off the ground, where it will focus its UV laser onto the soil and be able to detect chemicals that would indicate the presence of past life. The rover also has an X-ray imager called Pixel that will be able to visualize the texture of the ground below it, looking for tiny variations in geology that would indicate that microbial life has altered its environment, while also being able to detect chemical compositions by observing the fluorescence of the target under X-ray electromagnetic radiation. There are several other sensors, like the ground-penetrating radar imager located at the rear of the rover, which will give us visualizations of the composition of geology up to 10 meters under the surface, and possibly even identify water resources buried below, a vital resource for human missions. These are just some of the sensors on board, and of course, there are the usual high-definition color cameras that are going to send back amazing images to Earth, and this time we included a microphone so we'll be able to hear what our future life on Mars may sound like. It may even catch the whirring of helicopter blades off in the distance, because by far the most exciting part of this mission, to me, is the Ingenuity helicopter. After all, if successful, this will be the first time humans have demonstrated controlled, powered flight on another planet. Powered flight on Mars presents many challenges. The atmosphere is about 1% the density of Earth's, meaning there is less air to push down to achieve lift. To combat this, the propeller blades, which are counter-rotating to eliminate the need for a tail rotor, have to spin much faster than a traditional helicopter blade at about 2,400 RPM. That's about 5 times faster than an equal-sized RC helicopter here on Earth. To deal with the centrifugal forces that come with that, the blades need to be made of high-strength carbon composites. These blades also have a much larger angle of attack than your run-of-the-mill blade, allowing them to push a larger volume of air downwards. Since this helicopter will detach from the Perseverance rover, it needs its own power source. Unlike the planned Dragonfly mission to Titan, this helicopter will not have its own RTG. Creating an RTG capable of fitting into this tiny 2-kilogram helicopter is unfeasible. Instead, it features these solar panels, which will charge 6 lithium-ion batteries on board, and these in turn will power the motors and cameras on board, for a max flight time of about 90 seconds. This is simply a technology demonstration that will hopefully give NASA and JPL the information they need to approve and design a future flying rover. Today, the 18th of February 2021, is a historic day that I and many others will remember fondly for years to come. I remember exactly where I was and what I was doing when the Curiosity rover landed, and I remember seeing this man on my screen, a man who subverted my vision of what an engineer working on something this advanced was supposed to look like, Babak Firdausi. I could see myself being in his seat. He was relatable, not the white shirt, black tie, nerdy figure I had grown up expecting. I remember because I was a fresh college graduate, struggling to find a job, at a music festival, begging the organizers to put the landing on the big screens, but just ended up watching the livestream on my phone in a tent that was falling apart. I didn't fit the stereotype either. Today, on the historic landing of Curiosity's younger brother, I released an interview on Nebula with that man that I now somehow call a friend, talking about his career into JPL and what it was like becoming famous literally overnight. That interview is now available ad-free on Nebula, along with a whole host of new original content not available anywhere else. Mustard's new original called The Origins of Stealth, which details the fascinating history of the F-117 Nighthawk, a 3-part trivia game show made by Sam from Wendover Productions, and featuring yours truly, that really shows how distractible and unserious I am in person. These videos don't get my personality across at all. And of course, my 9-part Logistics of D-Day series. We are constantly adding more original content and ad-free versions of our YouTube videos, and all of that comes bundled with CuriosityStream for the low price of just $14.79 a year, a little over $1 a month. This is by far the best way to support this channel and get something in return with all of the amazing award-winning documentaries on CuriosityStream, like this fascinating biography of Neil Armstrong's life, narrated by Harrison Ford, and you get access to all of our original content on Nebula. If you are looking for something else to watch right now, why not watch my previous video about NASA's weird and wonderful oblique wing plane, or Real Science's latest video about the insane biology of ant colonies.